Good morning everyone. Thank you for joining Mr. Ish for today's video on vector algebra. This is one of those topics that will come in very handy as some of you will proceed into subjects like engineering and physics, because vectors are huge in that. This video serves basically as an introduction to vectors, and it may be split into two different parts with the basic concepts of vectors in this video and possible applications in the next. As a very quick precursor, these are two terms you should know, scalars and vectors. Though we're talking about vectors, it's important to know what a scalar is. A scalar is a quantity, like a numerical quantity, which represents magnitude only. It gives no indication or sense of a direction, but it only talks about the magnitude of that quantity. Take, for example, mass. If you weigh something, you get a term, you get a quantity, and that quantity is a magnitude of how much matter is in that item, right? The mass. Take it, for example, another scalar quantity such as length. Length only talks about the distance from one point to another, nothing more than that. How about temperature? The measure of kinetic or stored potential energy or thermal energy in an object. So scalars are magnitudes only with regards to the quantity. Example, as I've mentioned, mass, temperature, and length. But when we're talking about vectors, we're talking about something which has both a direction and magnitude. A force. Force is a very good example of a vector. Force, as we all know, is equal to mass times acceleration. There's a component of a magnitude in there, which is your mass, and there's a component of acceleration, which depends and implies a certain direction, a change. So keep in mind that vectors have both direction and magnitude, but our focus here is basically going to be on vectors. If this is a dot P which has an endpoint and it has a start point and it has an endpoint at Q, and this represents a vector, you know there's a bit of a direction involved and there's a magnitude involved. A vector PQ could be represented symbolically as this. But how do you show the magnitude and how do you show the direction of this line? If I'm saying that this line is a vector, then it must have a direction and magnitude. You can always represent the direction in terms of the horizontal. If this is our horizontal, whatever angle this is right here is going to give you a sense of direction. But how will you get a sense of magnitude for this vector PQ? Well, the magnitude can be represented by the length of this actual line. Think about it in terms of this. If there's a certain vector and it's called PQ, and it's represented by this line. I'm talking about here about magnitude, but then I have another vector which is called half PQ. How can I show the differences in the magnitude? Well, I can do the same line but make it half as long. So just by using the length of that line, that length, and halving it or a hair, we can get a sense of the magnitude. So lines which are representative here of vectors can indicate both direction and magnitude simply in terms of the angle and in terms of the length of that line. We can get both of those aspects for this vector. Keep this in mind as we look at examples over here and further concepts regarding vector algebra. Let's look over here. What's a zero vector? A zero vector would simply just be a dot, meaning you're going to have no sense of a direction over there. You'll have no magnitude. Your start point of this certain vector line and your end point are coincident. So there is a zero vector over here. This is what a zero vector looks like. Do not confuse zero vector for a line or a ray. A zero vector, you can represent it as a dot. Very infrequently seen, but just for your knowledge base, zero vector is represented by a dot. How about look, if supposedly u is represented by this vector line, how can I show minus u? Remember here, when we're talking about vectors, we're talking about direction and magnitude. Direction, as you know, is a certain angle theta, right? The certain angle with respect to the horizontal, that'll be your theta. So when you're showing these diagrammatically, you got to keep everything in mind. If this represents u, at the same inclination or the same slope, you got to represent the minus u but within opposite direction. You can't be representing a minus u of this vector in a line by a line of the same length but a different angle. It has to be in the same inclination. So keep that in mind. How about if I said minus half u? How would I represent that? It'll be with exact same angle with respect to the horizontal, but of course it'll be half as long. See, minus half u. If this is u, this is minus half u. You can represent vectors diagrammatically as I've shown you, and you can represent them mathematically. Triangle and the parallelogram methods are used to show diagrammatically how you can add two vectors. I want to show you some examples over here. Again, this is the diagrammatic aspects of vector, not as important, but important with regards to understanding. But the mathematics is more important than what I'm showing you here. Just look at this part I'm going to show you as part of your knowledge base. Alright, if supposedly u is a vector and it looks something like this, remember you got to keep in mind the angles and you got to keep in mind the magnitudes, the inclinations and the actual lengths. So do not sway away from those concepts. And if v is represented by a vector which looks something like this, I want to ask, or if someone asks me how can we show the addition of vectors, the triangle and the parallelogram methods are important when you're trying to add vectors. You can use these two methods to show by picture how you can add vectors. The triangle method is actually easy. You start with your first vector, which is u. You draw it exactly as you see it with the same inclination, same length. Then from the tip of that arrow, you do your next vector, the tip to the start. Here I'm going to draw my v vector, and you know v vector is aiming downwards. Now to complete the triangle method, you have to draw a resulting vector from the start to the end. The start of the first vector to the end of the second vector. That representing resulting vector is your addition of the two. It'll be u plus v. That's the triangle method. The parallelogram method is actually easy. Start with the u. Let me identify. This is my u, this right here is my v. The parallelogram method relies on you trying to draw a parallelogram. You start with your with the first vector you have. Right from the start of that first vector, you draw your other vector. So you're going to show two vectors, each originating from the same point. Now see if you can draw a parallelogram. You know a parallelogram has two pairs of parallel sides. Just draw like a proper parallelogram. See, I've got a parallelogram. From this origin, you connect to this point over here, and that represents your u plus v vector. Okay? The triangle method, the parallelogram method. I'm going to show some more examples of this diagrammatically before we get into the mathematics of this. Remember, vectors can be labeled by any letters. I'm just happening to use u's and v's over here. If u is a vector which looks something like this, and v is a vector which looks something like this, remember, keep in mind the magnitude and the inclination, the direction and the length. How can I show diagrammatically u plus v? I want to show you these using the triangle and the parallelogram method. The triangle method, let's show that. The triangle method, you draw your u, the first vector. Remember, from the end of the first vector, you must draw your second vector with the proper magnitude and direction. The proper magnitude and direction. From the first starting point to this last end point, draw your resulting vector, which will represent the sum of your two vectors, u plus v. This sum actually incorporates a direction and it incorporates a magnitude diagrammatically, and the resulting represents a u plus v. This right here is the triangle method. I'm going to show you the parallelogram method again. Parallelogram method, start with the first vector. Then from the starting point of the very first vector, draw your second vector in whichever direction it's supposed to be. And you know the direction by looking over here. Now you gotta draw a parallelogram to the best of your ability. Trying to keep everything parallel. See, these two lines are parallel, these two lines are parallel. Now from this first origination point to this intersection point of the dashed lines, draw your resulting, and that's your u plus v, the parallelogram method. This here is your resulting answer, the u plus v, the addition of the vectors with regards to the direction and with regards to the magnitude. Let me show you one more example before we switch gears a bit. I have a vector u. The vector u looks something like this. I have another vector v which looks, let's make this interesting, looks something like this. Keep in mind the inclination, the lengths, inclination and the lengths. I want to show half u minus v. The first thing we want to do, I want to show the sum of these two, alright? Remember, you can rewrite this as this. half u plus minus v. You see this? I've rewritten as this, so I'm making it into this form. Sometimes it can be a little tricky, but I want to show you these resulting vectors of this addition by the triangle and the parallelogram method. The first thing we want to do is generate a half u. If this represents a u, a full u, you know what a half u is going to be, right? A half u is going to be half of that, but with the same inclination, meaning the same angle, but half of it. What does a minus v look like? If this represents a minus v will be a ray or a vector of the same length but in the opposite direction. Same length and the opposite direction. So here are my two vectors which I need to use in this formula, half u plus minus v. So I'm basically finding the result of both of these adding together. The triangle method. Draw your u vector exactly as you see it. From the end of your u vector, draw your v vector exactly as you see this. Here's my v. Of course, I may not be drawing everything to scale over here, but I'm trying to be accurate. The start of the u to the end of the v represents your resulting, your addition. And here will be your half u plus minus v using the triangle method. I want to show now using the parallelogram method. First, draw your u vector as you have determined it to be. From the starting point of the u, draw exactly your minus v. Right here, minus v. That's your minus v. Okay? I should have put a minus v over here because this represented the minus v. Now draw a parallelogram to the best of your abilities. From this starting point, connect over here to this intersection of the two dashed lines, and that will be your resultant. Plus minus v. And here it's done. And look at these two lines. This was my resultant and here's my resultant. These two lines over here look identical. So diagrammatically, if you do all of these properly, your resultant will always look the same. Same length, same direction. If you think back to, or you rewind back to the previous two examples I showed you, and you'll compare the resultants from the both triangle and the parallelogram method, you'll notice them to look alike in terms of length and in terms of direction. If there's any inconsistency there, it's only because things are being drawn here using the hand, and hand can sometimes be imperfect in drawing. I want to switch now towards the mathematics of vector algebra next. If I have a vector, let's say u here and v over here, it starts from here and it ends over here at this coordinate, and this coordinate point over here is x1 comma y1, right? And this coordinate here is x2 comma y2. You can determine from this plot the horizontal and the vertical components. You know what the horizontal components always relate to, the changes in the x values, and the vertical components relate to the changes in the y value. So what's my horizontal component? Let's do some abbreviation. Horizontal component. Our horizontal component is basically going to be x2 minus x1. Easy, right? Horizontal component is always a change in your x. Your vertical component is going to be, of course, as you're imagining, y2 minus y1. Now you might be wondering, why is this important? Just to know the horizontal component of the vector uv. And you know, this right here is my vector uv. You can say it like this, or this entire vector can be represented like, say, let's use a capital P. You can represent it as this. Okay? Why do you have to know the horizontal and the vertical components? Because when you get into the application of these questions, especially in physics, and you're talking about forces, you have to determine the vertical component and the horizontal component of forces. You have to break down each vector into its components. And that's how you do it. You look at the horizontal components and you look at the vertical components. And there are various trigonometric applications or functions which apply to the horizontal component, and separately you have different types of functions which apply to the vertical component. So keep this in mind, how you can determine horizontal and vertical components. Horizontal is the difference of the x values, and vertical components are the difference of the y values. And everything we will look at now for the rest of this video will be in terms of the Cartesian coordinate system. And this is what the mathematical components for vectors will be similar to. Just like you can do operations with basically numbers, the various mathematical operations, you can do them with regards to vectors. Imagine if there's a vector, let's call that vector A, or let's, for consistency purposes, let's use u and v as I have been. If u is represented by, and this right here is a format of vectors. If u is represented by 1 comma 2 and v is represented by minus 3 comma minus 4, you can add and you can subtract and you can do various operations, multiply with vectors, and this is how you would do it. If someone said, show me the addition of vectors u plus v, remember the triangle method and the parallelogram method, that was the diagrammatic aspect of adding them. Now how do we do the actual algebraic aspect of adding? Well, you will do, over here you'll do x1 plus x2, x1 plus x2, that's your x component, and you'll do y1 plus y2, and that'll be your y component. You know, it's not hard. What's 1 plus minus 3 is a minus 2. What's 2 plus minus 4 is a minus 2. So just by doing this, you've shown that the addition of these two vectors is this new resulting vector. We will call resulting vectors as r, capital R. The resulting vector will be minus 2 comma minus 2. How about if you have to minus on u minus v? You do over here x1 minus x2, that's your x part over there, and then you do you'll do y1 minus y2. What are you going to get? 1 minus minus 3 is a what? 4. What's a 2 minus minus 4 is a 6. That's your u minus v vector. If you were subtracting v from u, you would get 4 comma 6 in terms of these coordinate systems. You can see scalars come into all of this too. A scalar is basically like a coefficient or a constant. What if someone said find 2u? Here the 2 represents your scalar. The scalar quantity was one which only had a magnitude, it never had a direction. But a scalar quantity can affect a vector. Look at how you do this. You do 2, 1 comma 2, and you get 2 comma 4. You see how the scalar here impacted everything in terms of multiplying with everything. How about if someone said minus v? Well, you know, that'll be easy. It'll be minus, and you'll do minus 3 comma minus 4. Right? Here's your scalar quantity of minus 1, and your resulting vector will be 3 comma 4. But what does it exactly mean? Let's look at this minus v. Let's look over here, v. If you plot v is minus 3 comma minus 4, what do you get? 1, 2, 3, 1, 2, 3, 4. Everything originates in terms of this from the origin. Minus 3 comma 4 would be a vector coming in this direction. That's my v. See, v is a minus 3 comma minus 4. But when I hit the v with a scalar quantity of a minus 1, you know, if you were drawing v in terms of a vector on a diagram, you'd flip it around. That represents the minus. Remember, minus is in everything is the same in terms of the magnitude. The minus just meant that the direction changed. You flipped it 180 degrees, you reversed it. But now let's draw v minus v, which is a 3 comma 4. Let's graph 3 comma 4 over here. 1, 2, 3, 1, 2, 3, 4. Now, of course, from the origin, shift upwards in the opposite direction. If this right here is my v, this right here is my minus v. And look over here, you can calculate the length of this from the origin to this point using the distance formula. You can calculate that. And again from 0 to the end of this distance formula. You'll notice that for each of these different separate vectors, the magnitude, which is the length, is the same, but the only thing which has changed is the direction. The direction has been changed by this minus. So you can see it right here very clearly. All we did was keep the magnitude the same, but we altered the direction. But how can you actually calculate the magnitude of any given vector? If you're given a coordinate pair, there's a specific formula for you to calculate the magnitude. The formula would be this. You want to use these type of vertical things. If I want to find the magnitude of u, the formula is this. This right here represents the magnitude. These two parallel lines means magnitude of whatever vector is in it. The magnitude of u is equal to the square root of the items within it. What are the items in it? x1 square plus y1 square. What are they? 1 square is a 1. 2 square is a 4. What do we get? Root 5. The magnitude of this is a root 5. What's the magnitude of v? The magnitude of v will be the square of the numbers within it. 3 square plus 4 square. 3 square plus 4 square, 9 plus 16. root 25, you'll get 5. The magnitude of this is a 5. The magnitude here can imply the length. Right? The magnitude here implies a length. And of course, there's a way of calculating the direction. We'll talk about that shortly. But remember, these formulas for magnitude are equal to this. The square root of the two components within it squared. You calculate the square root and you determine the magnitude. I want to present additional examples and concepts next. Let's focus our attention on the board to these two vectors. Vector A has coordinate 3, 8. Vector B has coordinate 5, 2. In terms of breaking down these, you can say this is x1, x2. You can say, x1, y1 and x2 and y2, or you can just use their individual letters. This is A1 and A2. This is B1 and B2 because these represent the B component vectors. So there's nothing wrong with how you want to notate your components so long as you stay consistent. You can say B1, B2. You can say A1, A2. Or, as I was saying, you can say x1, x2, and y1, y2 because these are the x and y coordinates. But staying now consistent with this technique over here, if you want to just find the addition of these two vectors, you know what you're doing. You're doing a1 plus b1, and you're doing a2 plus b2. So let's find the addition. The addition vector, adding vectors is easy. You're just adding the x, the initial, and then you're adding the secondary, the y component. What's 3 plus 5? That's an 8. Remember, this triangular bracket represents a vector component. And 8 plus 2, that's a 10. So that's just the adding. Now look at the dot product. The dot product, 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 represents the multiplication of two vectors. Now the formula is slightly a bit more complicated, and you lose the vector brackets when you're doing it. You're going to do 3 times 5, the first two, and you'll add them to the sum of the second two products. So what's 3 times 5 is a 15. What's 8 times 2? That's a 16. What do you get? 15 plus 16 is a 31. So the product of these two vectors gives you a quantity 31. You're not getting this now in terms of into a vector answer. You've kind of lost either one aspect. You've either lost the magnitude or you've lost the direction. It's kind of become a scalar quantity by multiplying. But this right here, the multiplication of vectors is very important in terms of applications. I want to present some applications over here. Example applications only. Like if supposedly u was a vector which was -4, -1, and v is 3, 3. How do we find the dot product u times v? Well, you just look at the formula over here. -4 times -3 is a -12. You add that to -1 times 3 is a -3, and you get a -15. -15. See, a vector has now become a scalar quantity. It has lost something along the way. How about this? If u is equal to 0, 0, which is basically a 0 vector of dot, and v is equal to 1, 1, you find the dot product. When you do the dot product of this, you're just going to get u times v is equal to 0. The vector has become a non-vector. It's become a dot. Okay, so keep in mind this right over here, the formula for finding the dot product. Why do you have to remember this specifically? Because now when we next look at how do we calculate the direction of a vector, you're going to use this formula right over here. And remember, I've already presented the formula for determining a magnitude. Let's look over here, the magnitude of vector A. A was always equal, the magnitude is always equal to the square root of the two components in it squared. 3 square plus 8 square. So what do we get over here? 9 plus 64. Let's bring the calculator out. We get 9 plus 64, 73. The magnitude of A is a root 73. So remember this. This right here is the formula for determining the magnitude. I'm going to show you next the formula for determining the direction. So keeping in mind what we've discussed so far in terms of vectors, the diagrammatic approaches, and what we've talked about with regards to the magnitude, very quickly, magnitude, as you know, if you have a vector, you can break it down into its x and y components, and you can determine the magnitude as a square root of the individual sum squares of those two components. And you know, magnitude is represented in this format. You can do the magnitude for as many number of vectors as we are going to deal with. But now talking about the direction, the tangent formula becomes very important when it comes time to deciphering the specific direction of a given vector. You know, tangent theta is always equal to opposite over adjacent with regards to a right triangle, y over x. the y component divided by the horizontal component, or you can think of tangent as being the sine divided by the cosine component. If you're looking at a specific, let's look over here actually at this u vector. You know, u vector with regards to a horizontal line, you can easily create a theta angle over here, and you can create a right triangle easily here. You'll have a specific endpoint component over here for this u vector, which would be u1 comma u2, right? The x component and the y component, u1, u2. The theta over here would be the y component, which would be your u2 divided by the x component. You do the arctan, the inverse tan. So you could think of it as doing u2 divided by u1, or y divided by x, or the sine component divided by the cosine component. You do the inverse tangent and you'll get that direction. Again, vectors of two dimensions have a magnitude and they have a direction. You have to determine and decipher both of those for any type of vectors that you deal with. As an additional bonus, we'll also be presenting in terms of an example form all of this, but we'll be talking about cosine theta and this specific formula. You know, this formula over here incorporates a dot product, u times v, the dot product, and it involves two individual magnitudes. This basically represents the angle between two vectors. If in addition to you determining the magnitude and the directions of this u vector and the v vector, someone asks you what's the specific angle between these two. Let's call this angle, let's give it like an angle, let's say theta 2, because just to differentiate it from this theta. You can clearly calculate the angle between any two vectors by using the dot product, dividing it by the individual magnitudes of the vectors involved, and then doing the inverse cosine or the arc cosine. Lastly, you have a vector v over here. See, we have a vector u, we have a vector v. If vector v had its own individual components, v1 and v2, which it does, you know you can easily calculate the magnitude, but then you'd also calculate the angle or the direction of this vector, again using the tangent formula. This tangent formula over here is the most important with regards to determination of direction of vectors. But don't always make the sense or the mistake of calculating direction specifically from the x-axis 0 degree or the 360 degree line. You can always use this minus x-axis, which also represents your 180 degree line, as your reference angle. You could calculate over here, this is going to be your y component, this right here is going to be a minus x component, here's your 90 degrees. You can always calculate the relationship of this angle right here or here. We'll call this like theta 3. You can always calculate theta 3 with regards to 180 degrees. You don't always have to look at 0 degrees. Another technique is if you have a specific example looking something like this, you can calculate the direction of the first vector, you can calculate the angle between the two vectors, and you can add both of these angles to give you the direction of the third vector. And remember, theta 3 would be equal to the sums of theta 1 plus theta 2. It would be with regards to the 0 degree line. Alright, so you have multiple ways. You can do individually using the tangent formula here with regards to your 180 degree reference angle, or you can do everything with regards to 0 degrees. Calculate theta 1, calculate this theta 2 using this cosine formula, then add both of those and get the direction for that third vector. Given all of this in mind, the magnitude, the direction, and the angle between two vectors formula, let's look at a few examples so we can put this into practice. So for this set of vectors u and v, we're going to determine individually the magnitude, the direction for each of these individual vectors, and we will also use that cosine theta formula to determine the angle between these two vectors. Always start with determination of magnitude where and when you can, and you know the formula for the magnitude is represented in this way. It's going to be the sum of the individual components squared and then the square root of those. 2 square plus 3 square, and you'll solve this out. And likewise for the magnitude of v, you'll do again the same formula, minus 1 square plus 9 square, you'll do the square root, and we'll get our determination for that magnitude of v. Of course, it's helpful to have a calculator over here. 4 plus 9, root 13. We don't have to actually get into decimals. 1 plus 81, root 82. Don't even bother simplifying these. Leave them as is. Now, it's never a bad idea to diagram these or plot these, because it gives you an indication of what quadrants you're dealing with. 2, 3. That's my u vector. It's going to be over here. Minus 1, 9 is going to come all the way up over here. Let's not worry about too much of scale. So here's my v, here's my u. We need to determine the angles here of all of these. How are we going to determine the angle of u? Well, the angle of u is going to be represented right over here. We'll just do the tan theta formula. tan theta formula is equal to the y component or the x component. You know the y component right here is the u2 or the y aspect of this vector. So you just do 3 divided by 2 and you arctan it. When you arctan 3 divided by 2, you'll get a very good answer. You get 3 divided by 2 inverse tan, you get 56.3 degrees. So the direction of this specific vector u is 56.3. It has a magnitude of root 13 but has a direction of 56.3. Let's do the same for the v. You know you're going to do again the tan theta formula. Very wonderful and convenient formula because it employs a relationship between y and x to determine the angle. So here tan theta is equal to 9 divided by minus 1. See the y component divided by the x component, or the vertical component divided by the horizontal component. Bring out a calculator here because you'll do it. You'll do minus 9 because 9 divided by minus 1 is a minus 9. Inverse tan, you get a minus 86. Actually you get a minus 83.6 degrees. Now minus 83.6 degrees has to be determined with reference to some horizontal. You either can use a 0 degree horizontal, which is also the same as 360, or you can use as 180 degrees horizontal. Because v is in the second quadrant, we should use 180. All you do is minus 83.6 add it to 180 plus 180 and it gives you an angle 96.3. So our true direction is 96.3 degrees. Now this is 96.3 degrees with reference to 0 degrees because you're going to go in this direction, alright? You go in this direction, that'll be your 96.3 degrees. And you know the u is 56.3. This right here is 56.3, that's 96.3. If you minus these two, you can of course get the angle of the two vectors, the angle in between the two vectors. The large angle minus a small angle, you can get this intermediate angle in between. But I want to use the formula specifically. Remember the formula was cosine theta is equal to u times v over the individual magnitudes of the two vectors, the dot product divided by the individual magnitudes. But what's a dot product? You know the formula u1. Let's actually write it out. The dot product is equal to u1 v1 plus u2 v2. These products individually and squaring them in between and summing them in between. By squaring I was meaning summing them. Okay, so let's do u1 v1 plus u2 v2. u1 v1 plus u2 v2. 2 times minus 1 is a minus 2. You get a minus 2 over here. 3 times 9 is a 27. What am I getting? You're getting a 25. Now all you gotta do is plug in the values over here. Cosine theta is of course equal to dot product, which is 25 divided by the individual magnitudes. Root 13 multiplied by root 82. Remember we're right now working for this cosine theta angle, the angle in between the two vectors. Do this computation and then do the inverse cosine, because theta will be equal to the inverse cosine or the arc cosine of this value over here. Let's bring that calculator. 25 divided by root 13 divided by 82 square root, and you inverse cosine it and you get an angle which is 40 degrees. 40 degrees. You could have easily done 40 plus 56.3 and given you that 96.3, the direction of v, or you could have easily done 96.3, the longer angle, the v, minus 56.3, the u direction, and gotten that intermediate answer 40. But here I was just trying to show you the various formulas which are involved. The u is here. The u direction has a value of 56.3 degrees from 0 degrees as your reference on horizontal. It has a magnitude of root 13. The v vector, it has a direction of minus 83.6 degrees but from 180 horizontal, or it has a direction of 96.3 degrees but from the 0 horizontal, and it has a magnitude of root 82. The intervening angle between these two vectors is 40 degrees. Not a hard question. Remember, you can't always be used to examination of vectors always in quadrant number 1. Sometimes you have to look beyond quadrant number 1 and see which type of reference horizontals you have to use to start thinking beyond just quadrant number 1 type of questions. Let's look at another question which again will not be relying solely on quadrant 1, and then we'll end this video with that last example. Here is that last example. Should be an interesting one. We're going to determine, after the review of the previous formulas, we can review those in our head. We're going to determine the individual magnitudes, the individual directions. We're going to determine the intervening angle between both of these two vectors. Remember, you know the formula for determination of magnitude. you know the formula for determination of the direction involving the tan, and you know the formula for determination of the intervening angle using the cosine theta formula. You can always manipulate the numbers, and you can use both numbers as reference to determine the intervening, or you can use two individual angles that you already have to determine the third by taking the sum or the difference, as I was showing you in the previous example. Or you can just keep everything formal and use the formula specifically. Let's look at the magnitude of u. The magnitude of u, given this notation, will be equal to the square root of minus 2 squared plus 2 squared. You know that's going to be root 8, but we will simplify that as 2 root 2. V magnitude, vector v, is going to be minus 3 squared plus minus 10 squared. Remember, it's always the horizontal square component square plus the vertical component square and the square root of that. And you know you're going to get 100 plus 9, you'll get a root of 109. The direction. The direction, of course, as you know, is always the tan. Let's do tan theta is always equal to, let's do y over x. But we can rewrite this, as I was verbally saying, you can rewrite this, theta is equal to inverse tan, or the arc tan. See, arc tan. Inverse tan, arc tan, same, y over x. Or you can say the sine component divided by the y component, the cosine component, or the vertical component divided by the horizontal component. What is the angle for vector u? It's going to be 2 divided by minus 2, which will be a minus 1. 2 divided by minus 2 is a minus 1. You're going to do arc tan of minus 1 on your calculator and you get a minus 45 degrees. But look at this. Minus 2 comma 2 gives you an indication of a second quadrant angle right here, doesn't it? If it's minus 45 degrees, it's minus 45 degrees with reference to 180. 180 minus 45. So you're going to go minus 45 in this direction. 180 minus 45 will give you 135. You know 135 is 3 pi over 4. 135 degrees. Anyhow, magnitude of vector u is 2 root 2 with the direction of 3 pi over 4 or 135 degrees. When you have this minus 45, I mean it's with reference to 180, but the fact that we adjusted it, by adjusting it, you made it with reference to 0 degrees. Vector v direction. Let's write arc tan this time, just for a little difference over here. Minus 10 divided by minus 3, the y component divided by the x component. It's really just 10 over 3 because the minuses cancel. Do 10 divided by 3, you get 3.333, and you inverse tan that, you get 73.3 degrees. Theta is equal to 73.3 degrees. Now we have to determine what does 73.3 really mean. But plot it out. Minus 3 comma minus 10 would be a third quadrant vector. Here's my u, here's my v, third quadrant vector. You know you're not really looking at a 73.3 in the first quadrant, but you're looking at 73.3 with reference to this 180 degrees. You're going to do add it to 180 degrees to get your proper third quadrant angle. 180 plus 73.3 will give you 253.3. 253.3 degrees. Theta for vector v, 253.3. This 73.3 was with regards to reference of 180, but this 253.3 is with regards to your 0 degree line. Look at this. You're going all the way up over here to give you 253.3. Now the intervening angle between can just be 253.3. You can just do 253.3 minus 135 and you get an intervening angle of 118.3. You get an intervening angle of 118.3. The intervening angle meaning the angle between the two vectors u and v. But let's use the formula. Cosine theta is equal to the dot product of the two vectors divided by the individual magnitude of the two vectors. And using this product and the inverse cosine, we should get 118.3. Because I wanted to keep it formal and use the formula specifically. The dot product will be u1 times v1 plus u2 times v2. Let's do that over here. Instead of writing out, let's do it. Minus 2 times minus 3 is a 6 plus 2 times minus 10 is a minus 20. We get a minus 14. My dot product is a minus 14. My magnitude for u was a 2 root 2. My magnitude for v was a square root of 109. You're going to take this little calculator product and you're going to do the inverse cosine to that and you'll get something very close to 118.3. If we've done this correctly, we will get that. Minus 14 divided by square root of 8, which is same as 2 root 2, divided by 109 square root. I get a minus 0.474, inverse cosine that, I get 118.3, so we're good, 118.3. Our intervening angle between vectors u and v is 118.3. You could have determined that formally using this formula over here, or you could have just taken the difference of this vector v direction and the vector u direction, because the difference in between represents the angle in between. Or you could have determined cosine theta, this intervening angle, and you can have determined the u angle and then determine the v from adding both of these. You see, if you determine the u direction and you determine the intervening angle, you just add them up and you get the v direction. You would have just done 118.3 plus 135 and you would have gotten 253.3. So there are multiple ways. I was just trying to keep it formal because I was introducing these formulas for this vector algebra video. So keep in mind the very important formulas that I've presented. Of course, always keep in mind the formula for the magnitude of any vector, the sum of the horizontal and the vertical components squared and the square root. That'll give you the magnitude. And always keep this in mind. The inverse tan or the arctan of the y component or the x component gives you specifically the direction of the vector you're looking at. Always be wary of whether your answer is presented with regards to which horizontal line. Is it 180 or 0? You can adjust accordingly. And lastly, you can always keep this in mind. The angle between any two vectors is dependent on this formula right here. But this formula over here requires you to be familiar with the dot product. And dot product, you know, is u1 times v1 plus u2 times v2. Okay? Keep all of these aspects in mind. And everything I presented previously with regards to the triangle and the parallelogram method. So this is pretty much my video over here for vector algebra. Think of it more as an introduction, because in the next video we'll be looking at specific applications of these. I will probably present like a review video at the very end, like a third video, and that'll be the end of the vector topics. But feel free to look at this video several times. I hope you liked this video. I did. And please like, subscribe and share. Have a nice day. Bye.